A very good day to all. Welcome to the class of PSCAD. We are in week 4 and we're supposed to go into chapter 3 today. Okay, let's go to our plan that we have set earlier in the beginning of the semester. Okay, right. If you look at the plan, we are just going in accordance to the plan. So we are now in week 4. So we enter chapter 3 today on the simulation of reactive process, right? And in terms of assessment, I think almost every class, after every class, you have the sub-quiz. And the sub-quizzes in chapter 1 and 2 will make up to your mark for quiz 1. Okay. I think by next week I can release the marks to you, then you can check for it. And within this week, the assignment 1 also will be released to you. Okay, it will be released on 11th of November, and you're supposed to submit it by 25th of November. Okay, assignment 1 will be having 2 questions. The first question is covering chapter 1 and 2, while the second question is covering chapter 3 on the simulation of reactive process. Okay, done for the planning. Just a revision for you, or just to remind you on the plan and also the assignment that you have to perform later on. Okay. So done for the plan. Then we move to the slides today. On the simulation of reactor using the model in Xpen Plus. Okay, there are 3 types of reactor model under Xpen Plus. They are balance-based reactor, equilibrium-based reactor, and also kinetic-based reactor. So typically, in a chemical process, we will have the reactor as the core unit operation. Okay? So of course, before the reactor, we have the separator to pre-treat the raw material so that the contaminants that can deactivate the catalyst in the reactor can be removed prior to the reaction. So after the reactor, as usual, we would like to produce the product up to certain purity. And in order to do so, you need a series of separator to purify the product from the reactor. To solve the chemical reaction engineering problem, as what you learn in CRE, I think most of you maybe are taking CRE 2, but you have learned all this in CRE 1. Okay, the knowledge that required is, of course, thermodynamic, reaction kinetics, engineering economics, heat transfer, mass transfer, and also fluid mechanics. It requires a lot of fundamental knowledge, right? And I think in CRE 1, you have actually utilized the knowledge in thermodynamic, reaction kinetic, fluid mechanic, and also heat transfer. But in CRE 2, you add one more, which is on the mass transfer, and that are related to the diffusion that you learn in if you are using Faulkner textbook, it is in chapter 12 and 11 and 12 on the external and also internal diffusion. So that are related to mass transfer. Okay, you need all this knowledge for the reactor design. So of course, in order to solve the chemical reaction engineering problem, we always start with the more balanced equation, and that is exactly the mass balance equation. You can solve the mass balance equation using the basis of atomic species balance, okay, or either based on extent of reaction or the molecular species balance. So this is how you solve the mass balance for a reactor. You can do it manually, and of course in this case, with the introduction of this chapter, you are able to simulate the reactive process using X1+. It can expedite the process to get the reactor design. So this is the typical algorithm for you to design a reactor. Just to revisit what you learned in CRE1 last time. So you always started with more balance, that is a mass balance equation. Different types of reactor, of course, the mass balance equations are different. So we have PFR, plug flow reactor, CSCR, continuous tank reactor, and also batch reactor. And after you have the more balance equation or mass balance equation, then you have to state the rate law to represent the reaction happen in the reactor, and you have the stoichiometry to relate the parameters in your mass balance equation with the concentration or molar flow rate profile in the reactor. And once you have all these three basic elements, if it doesn't involve any what we call the heat transfer process, then you can actually combine all these basic elements and solve it accordingly. So the steps are here, you combine and solve it either numerically, or you can use software like Polymath or MATLAB to combine all these equations. Okay. So upon the completion of this chapter on the simulation of reactive process, you should be able to introduce various classes of reactor models in X1+, and able to simulate the reactive process using different types of reactor model and analyze the simulation results. So with the introduction of the software, you are able to solve the chemical reaction engineering problem without doing it manually. Just use the software to speed up the progress. So as I mentioned before, there are three types of reactors model. So we have a balance-based model, which includes R yield and R stoich. And we have equilibrium-based model, includes R equal and R gibbs. And we have the kinetic-based model, and this includes RCSTR, R plug, and also R batch. All these terms are the reactor model available in X1+. Of course, one point to emphasize here is the last types of reactor model, the kinetic-based model, are the more rigorous models, and it requires more information when you want to use it, especially the reaction kinetic, or we call it rate equation, to represent the reaction that occur in the reactor. A little bit description of each type of model here. So we have R stoich and R yield for the balance-based reactor, and our focus would be on R stoich, RCSTR, R plug. So our focus will be on these three, but the other will be introduced to you in terms of its description and also limitation. Later on, when you are doing your plant design in the future, then you may need the other model, depending the information that you have in hand. If you have limited information, then you may need to go to certain model. But if you have substantial information, then it's not a problem for you to go for the kinetic-based model like RCSTR and R plug. So let's move on. So we will go for the equilibrium-based model first. So this is just introduction to you. So this reactor do not take reaction kinetics into account. and solve similar problems like the other reactor model, and allow individual reaction to be restricted, to be at restricted equilibrium. So if you are using the equilibrium-based model, all the solution will be based on the equilibrium. So either chemical equilibrium or phase equilibrium, or it can be a combination of these two. But of course, there are some limitations, like R equal over here. We have R equal, one of the equilibrium-based model. One of the limitations is it cannot do the three-phase flash, meaning if you are having vapor liquid equilibrium, you cannot use R equal. So those are the limitations that you need to take into account when you want to select the reactor model in X1 Plus. So the other type of equilibrium-based model is R-Gibbs, and the solution of R-Gibbs will be based on the minimization of Gibbs energy. And one point over here is if you have unknown reaction, then it is actually quite good for you to use R-Gibbs. Meaning, if you are having limited information on the reaction, then just use R-Gibbs. And one of the advantages for R-Gibbs is it can handle solid equilibrium. Meaning, if you are having solid, liquid, and gas phase equilibrium, so you can actually go for R-Gibbs. We move on to balance-based reactor. So for this type of reactor, under this category, we have R-yield and also R-stoid. And our focus will be on R-stoid. But just to introduce to you what is actually R-yield. R-yield requires a mass balance only, but not atomic balance. It is used to simulate reactor in which inlet to the reactor are not completely known, but outlet are known. So in this case, there is one example over here. Based on the flow sheet given, you have the details for the product, but you don't have the details for the raw material. Raw material here is coal, and it is a very complex compound, and it may be a mixture of CH and CNH. It's a hydrocarbon, or it's just carbon. Okay? So if it's a complex compound, so you can actually represent it using what we call pseudo compound. We can call it pseudo compound, not a real compound. And of course here, we don't have enough information for the feed. In this case, you can go for R-yield because you have the complete information for the product. For R-stoid, this is our focus. It can be used to solve the reactor with the simultaneously and sequentially reaction, meaning is parallel reaction and also reaction in series, meaning R-stoid can handle the complex reaction, and it can be used to perform product selectivity and also heat of reaction calculation. Based on the flow sheet given, I think the heat stream or the energy stream here is optional, but the mass stream here is compulsory. You can also handle, if you are having two immiscible liquid, the liquid equilibrium, you can also have the water decant here. Okay? Let's say you are having a mixture of water and hydrocarbon, then of course you may have two layer form. If it's liquid, then you can have the stream for water. R-stoid require both atomic and also mass balance. This is slightly different from R-yield just now. R-yield just required the mass balance, and it is used when both equilibrium data and also kinetic data are not known. Okay? And we can specify or calculate the heat of reaction at a reference temperature and pressure. So this is what RSTOID can do. Okay? So of course, we have the example over here. So probably this is a combustion process for you to produce. Yeah, normally it should produce, I think the aim for this process, the one showing here, is to produce CO2, right? So the oxidation of carbon, simple process. So we start example 3.1 after a 5 minutes break. Thank you very much.